Hello, my name is Alessio Rovere and I am the principal investigator of the Warm Coasts project. In 2019, just at the beginning of the project, we were doing fieldwork in Argentina. Bahia Laura is a very special place. There are beautiful strand lines, beautiful shorelines, showing you that probably the coastline has rotated since the last interglacial. It was a very difficult trip to organize because there was a lot of logistics involved. We had to sleep in a place and drive 1 hour and a half every day to go back and forth Bahia Laura, but we finally reached this place. And with us, there were the Argentinian colleagues who have been collaborating with us all the way. And they brought a key instrument to understand how shorelines evolve in time, which is called ground penetrating radar. Now, everything was working very well. When we go on modern shorelines or on shorelines that are not as old as the last interglacial, we see under the surface, this is what the GPR allows you to do. We were seeing beautiful shorelines evolving through time. But when we go to our target period, what we found was that the GPR could not read under the ground. Probably something in the ground wasn't responding well, and we could not get what we wanted. The feeling at the time was quite bad, and these are moments in a project where you wonder, what are you gonna do? Mistakes are in a way the engine, though, of scientific research. And the setback that we had in Bahia Laura will finish some time later in a success in Florida. But before I tell you about this story, let's take a step back at the beginning of it all. The Warm Coast project addresses three main questions. The first one is to understand whether sea levels were higher during the last interglacial, which is a period of time when the Earth was warmer than today. The second question is if sea level during this period was oscillating, so giving rise to sea level rise rates higher than today rates. And the third question is to understand whether waves were stronger than today in this warm period. And these questions have a direct bearing on the coastlines of today and on the population living on them. Just after we started to go out in the field. We were in Bahia Laura. We had this big success. We were trying to recover from that. And all of a sudden, something big happened, which was, of course, COVID.
I came from Mexico to do my PhD in Germany. It was already a bit late. But just as I settled in, COVID hits. As a field scientist, to don't be able to go outside to work, it was incredibly frustrating.
Luckily, there was one silver lining, which is the first action of the grant was putting together a database, this big database, which we call WALIS, the World Atlas of Last Interglacial Shorelines.
WALIS isn't just a database, it's a springboard for new research. Imagine a global map showing where oceans stood 100,000 years ago. That's WALIS. It's a powerful open access database that collects sea level records from around the globe, all focused on the last interglacial. Scientists use it to reconstruct ancient coastlines and better understand how sea level responded to warmer climates.
Finally, the pandemic stopped. We were allowed to travel again, and so we set our sights into another place, which was Florida.
I was not there for the fieldwork in Argentina, but I was there in Florida. We arrived in Florida after a very long flight, and then a drive from Atlanta through 3 or 4 states, and then we started setting up the GPR.
A ground-penetrating radar is a tool which uses electromagnetic waves to map what's beneath the surface. It sends short pulses into the ground and records the signals which bounce back from buried layers. In the coastal studies, we used GPR to map ancient beach structures which are buried beneath the surface. These paleo beaches help us reconstruct the past sea levels and understand how coastlines have changed over time, and consequently, how climate have changed over the time.
The East Coast of the United States is an extremely developed area. So you try to find a site where you think the sediments and the stuff underneath the ground is going to be undisturbed by people. And you go there and sometimes it's just nothing, just static. And then finally we got to this place, a field basically. There were some cows in the distance you could see, and it was just perfect. We could really see these ancient shorelines, these reflections of different layers of dunes, of beach faces, and it was a very gratifying moment. We got what we're looking for. This is something that can push forward science.
Actually, we realized that the beaches we were intercepting with GPR were cut into half by intracoastal waterways, which is an artificial channel that allow us to navigate on the east coast. This means that we can assess those deposits without digging and coring. We bring the samples to the laboratory, and we are using different methodologies to constrain the paleo-environmental conditions. We are focusing mostly on the organism, which is specifically foraminifera, which is one of the best indicator for the paleoclimatic reconstructions, and they are actually giving us a whole climatic history.
My duty was to analyze and to derive sea level information from the sediments outcropping and to see if there could be some fluctuation. In general, the classic view was that the sea level was quite stable. We expected to find just one peak of Mayas 5e, but what we are discovering during this project is that more fluctuations are preserved in that area. The most important factor was to date the sediments.
You also need some geochemistry in your toolkit. For example, we can use something called amino acid racemization to date mollusk shell. When an organism dies, its proteins begin to degrade. Like a ticking clock, we can measure those changes to estimate the age of the shell. This can be used to help us pinpoint the timing of past sea level events.
I'm a geologist and geomorphologist, so in this project I used my experience with surveys of outcrops, going out to some place, cutting back the weeds and the plants that are in the way, hitting the cliff with a hammer, extracting samples, this kind of thing. And so when sands, which are primarily quartz, are exposed to the sun, this exposure to sunlight changes the nature of the electrons in the sands. This is a simplified version of it, but that's the main gist. So if you bury the sands, it sort of freezes in time the moment that they were covered. And there are certain scientific analyses called OSL dating, optically stimulated luminescence. And in this way, you can get a date of when the sands were submerged, when they were buried underneath other sands, and that's what we're looking for.
What are we left with at the end of this project? Do we know more about how high was sea level during the last interglacial? Well, yes. While we thought before that sea level was probably 5 to 10 meters higher than present, now we think that it was probably a bit lower, let's say 2 to 5 meters higher than present. This might seem like a good news, but if you think about it, even 1 meter of sea level rise is very dangerous for our world. The second question was sea level oscillating during this period? And this talks about the sensitivity of ice to slight warming changes. Well, the answer to that is a little bit less direct, because some data would show us that yes, we had some oscillation of sea level, but we cannot understand if these oscillations were due to local processes or to global processes or to ice processes. But we did a step forward in the right direction. And the same thing with models of reef growth and demise during the last interglacial.
We ran nearly 50,000 simulations of coral reef development under different scenarios. We found that emerged backstep reef features like those in Yucatan can only be explained by a first sea level peak, followed by a pause or even a drop, then an abrupt rise and a second short-lived peak. But not all step morphologies need rapid sea level changes. Some can result from erosion, reef growth, or the shape of the underlying bedrock. So interpretation really depends on both context and careful modeling.
Now, were waves stronger than today in the last interglacial? As a surfer myself, this is a very interesting question because I want to know if in the future my sons or my nephews will be able to surf better than I can do today or better waves. Well, on the other side, I must say that it's a very dangerous thing to have waves hitting on our shorelines in a more powerful way than they do today. In some locations, we could understand that there are a bit more frequent swells than we have today, but again, the jury is still out. We did steps in the right direction and we could answer some of the questions locally. So this project was basically assembling a number of local stories in terms of geology to try and answer global questions. But in the end, I think the more important thing of this project was the people we are working with. We worked with people from all around the world, and basically this is the real value of what we did. A little bit like a jazz band playing together for one beautiful symphony.